occasion you're going to have compound things that you might need to figure out the moment of inertia for. So again, to do this, again, you divide it up into simple shapes. And the examples in the book, they also give, and I'm just following those. Example 1 says you find the value of the moment of inertia for a 6x12 wood beam about an axis through a centroid, which is in the center, and parallel to the base of the section. So for this simple 6x12 inch beam, remember wood, you have to look up the real dimensions because a 6x12 is not really 6x12, it is 5.5 by 11.5. And then, and they found that information on the page. Back in the end of the chapter, there's some tables. It says table 10.6. Which is on page 210. Talks about the dimensions of wood. You may need that in some of your future problems. So you find the exact dimensions. Then you know that if you also look on page 201, there's some formulas that you can use to figure out the moments of inertia for these simple shapes. So when the reference plane passes through the centroid, you're going to use I, which is, if I'm looking on page 201, I equals BD cubed over 12. Now, note though, to the right, if the reference plane is at the bottom, you're going to use a different formula. See that I is down at the bottom of that shape. So if it's here, through the middle, through the centroid, it's going to be, on page 201, it's going to be I equals BD cubed over 12. But if it's down here, it's going to be I equals BD cubed over 3. And that's true for all of those rectangular shapes. So that's simple. You just figure out 11. You say 5.5 times 11.5 over 12 equals 6.97.07 inches to the fourth. So that's, a simple way. So then, now that you know how to do the rectangles, then you're going to come down and do this more complicated shape. It says find the moment of inertia for a 6x4 by 1/2 inch angle. It gives you the in figure 10.5 about its neutral axis, and they've already figured that out for you. And it's going to be this line, which is 2 inches above the bottom. And they've given you these dimensions. So what do you need to do? First you need to divide it up into different parts. So you're going to say you divide the section into three different parts. And this line is important because that's the rotation point. So that's going to be one of the parts. So you're going to have a part here. Oops, I did that wrong. This is going to be one of your parts there. Then your next part is going to be, this whole triangle, and then you can subtract out the negative space. See if this paint thing works. So you got that part. Oops. Then you've got the white part, and then you've got this pink part. So you want to find the moment of inertia for each different part. So let me text. So the first part we're going to do is this one up here. And from our formula before, we know that the I is going to equal, because our reference plane is at the bottom of that rectangle, we're going to use the one divided by 3. So I equals BD cubed. I don't know how to write cubed in the thing. Oh well. BD cubed divided by 3, which is going to equal the base, which is 0.5 inches, 0.5 times the height or the depth, which is going to be 4 inches, and that's cubed. 4, I'll do it like that. 4, oops. And all of that is going to be divided by 3. So then that also equals what they have in the book, which is 10.667 inches to the 4th. Everybody follow that? So this moment of inertia up here is the base times the depth or the height cubed over 3, which is 0.5 times 4 cubed over 3, which equals that. So we got one component. Now the next component, we're going to do this whole section. So we'll do, let me skip one more line. You got the moment of inertia equals, again it's B, because the reference plane is on the top or the bottom, BD cubed over 3, which equals, that's supposed to be an equal. Ah, crap. Let me fix that. So that whole bottom square, all of this is going to be, the base is 4 times, the height is 2, and that's cubed. And that's going to equal, all of that divided by 3 equals, again, 10.667 inches to the 4th. Now, we got to subtract this part. So that moment of inertia for the little part is going to be equal, again, to BD cubed over 3. I got the formula from the back. If you have other shapes, you need to use the other formulas, which is going to be equal to 3.5, which is the base, because we took off the ½ inch either way. So it's going to be equal to 3.5 times the depth of the height, which is going to be 1.5 cubed over 3, which equals 3.938 inches to the 4th. 3.938 inches to the 4th. And that's going to be a negative. So so then to figure out the total moment of inertia, you just say 10.667 plus 10.667 minus 3.938 is going to give you 17.396. So that way you figure out the moments of inertia for the littler ones, and then you add and subtract and get the bigger ones, or the whole thing. Does that make sense? Pretty simple. You can use these formulas. You might want to copy them or do something with them. The ones in the back of the book. I don't see where, as an architect, you would ever need to, get into crazier shapes than these. You can usually break it down into those simple shapes. So for the homework on this section, and again it's written in Canvas, you're going to do the problems 10 on page 193, 10.3a, and 10.3b. Is there any questions? No? Completely understand it. Okay, I want you to do the homework before Tuesday. You can either hand it to me on paper during our first class, or you can scan it and send it to me online. And then our Tuesday discussion will be over the remainder of the chapter online. Okay? And no more, there's no questions?
What were the questions that?
Well, it's written on Canvas, but it's you're going to do on page 185 problem 10.1a and 10.1b, and on page 193 problem 10.3a and 10.3b. Plus, you need to work on your exam if you want to bring your grade up.